We're live. Looks like there's just a few of us right now, so we'll give it a couple of minutes before we start doing some problems. I hope everybody's having a good day today. So in the description, hello T-Zone C. Good deal. We'll get started in a minute or so. In the description, you could see the questions that we're going to work through today. We're not going to get through all of them, but we'll get through a good number of them. Hello, Cup. Welcome, welcome. Yeah, so take a look at those questions, and if I already have a list of some questions that some of my students will refer first, so we'll go over the ones that my students want to go over first, because they're my students. But if you guys have questions you want to go over also, we can do that. Cookie Man, good to see you. Hope everybody's doing well. We've got beautiful weather here today, so probably hang out outside after this. Okay, well, let's get started. So the way I start my class, if you don't know, is with the simultaneous sip. So if anybody would like to join in on the simultaneous sip, doesn't take much. Coffee, water, juice, whatever you're drinking, now's the time to do so. I got water because it's 5 o'clock. Yeah, Black Pen, Red Pen was live the other day, me today. Yeah, you can get a lot of good calculus for free on YouTube nowadays, which is awesome. Okay, let's start with number 1 because that was requested. So what's the, we have a test, my class has a test tomorrow. It's on optimization, related rates, implicit differentiation, linear approximations, and curve sketching. That's a lot of topics, so we're gonna try to cover a little bit of each. My brother made it just in time for the sit. Excellent. Okay, so let's start with number 1. Number 1 is an implicit differentiation question. It says we have this curve x squared plus xy plus y to the third equals 1. Okay, so we have this curve x squared plus xy plus y to the third equals 1. We want to find y double prime when x equals 1. Okay, so find the second derivative. Find the second derivative when x equals 1. Okay, and so we're going to just take the derivative a few times. So let's start by differentiating both sides, right? So the derivative of x squared is 2x plus, okay, what's the derivative of xy? It's xy prime plus y, right? This is the product rule here. The derivative of xy, we have to use the product rule. So it's first times the derivative of the second plus the derivative of the first, right? The derivative of x is just 1 times the second plus 3y squared, okay? Chain rule, y prime equals, okay, what's the derivative of 1? It's 0. All right, so we want to find y double prime. We could either just take the derivative again and try to get y double prime by itself, or we could first get y prime by itself and then just take the derivative of both sides. So let's do that. Let's get y prime by itself. Okay, so we'll keep everything that has a y prime on the left side. Everything else will go to the right side. All right, and now we can factor out a y prime. And we have x plus 3y squared here we have minus 2x minus 1. Okay, and to get y prime by itself, we just divide. Y prime is equal to negative 2x minus y over x plus 3y squared. Okay. So that's y prime. The question asks for y double prime, so we have to take the derivative again. But that's not that big of a deal. Okay, so another derivative. Left-hand side, we just have y double prime. That's what we're looking for. And to take the derivative of this, it's a quotient, so we use the quotient rule. Bottom times the derivative of the top minus the top. I guess I'll have to go on to this next board, times the derivative of the bottom, which is 1 plus 6y y prime, all over the bottom squared. Right, so this is the second derivative of this curve at any x and y value. We want to find what the second derivative is when x equals 1. Okay, and so if we look at our equation for y double prime, we need x, we need y, and we need y prime when x equals 1. So let's first find y when x equals 1. The way we could do that is we just plug x equals 1 into this original equation, so I'll do it up here. So 1 plus y to the third is equal to 1. Solving for y, we have y to the third plus y equals 0. So y times y squared plus 1 equals 0. There's only one solution, and that's y equals 0. Okay, and to get y double prime, we can plug x equals 1 and y equals 0 into this equation here. So y prime of the point 1, 0, so the derivative at the point 1, 0 is negative 2 minus 0 over 1 plus 0, which is negative 2. Okay, and so now to find y double prime when x equals 1, we just have to sub in x equals 1, y equals 0, and y prime equals negative 2 into this big equation here. Okay, and so let's just do that. Okay, so x equals 1, y equals 0. So that's going to be 1 plus 0 times negative 2 minus y prime, which is also negative 2. Okay, that's 0. Minus, okay, negative 2 times 1 minus 0. 1 plus 0 all over the bottom squared. Which is 1 plus 0 squared. Okay, so let's clean this up a bit. I know my spacing on this board isn't very good, but y double prime of the point 1, 0. Okay, this term goes to 0 minus, this is 1, so this is 2. All right, there you have it, 2. Okay, let's recap what we did here because I know it was kind of fast. So we wanted to find y double prime when x equals 1. Take the derivative, use implicit differentiation to get y prime, right? Get y prime by itself. So take the derivative of both sides, keep everything with a y prime on the left, everything else will go to the right, factor out the y prime, and then divide to get y prime by itself. Take the derivative of both sides. That required the product and chain, the quotient and chain rule. Not a big deal, we're experts at that at this point. And then just plug in the appropriate values. So we knew x equals 1, we found y is equal to 0 using the original equation, and we found the derivative at that point 1, 0 is negative 2 by just plugging it into our derivative equation. Okay, and then you plug all the values in and you get to. All right, that's question 1. I see my autofocus is on. That's kind of annoying. I thought I turned that off. So yeah, sorry if it keeps going in and out of focus while I move. I'll have to turn that off for the next one. Okay. So feel free to just type in the chat if you have any questions you want to go over. But I have this list of questions from a student, so I'm going to continue doing those while the list exists. So next, I'm going to work through number 10. Okay, it's okay most of the time. The autofocus, yeah, but it would be better if it was just off all the time. So next time I'll fix that. Okay, number 10 says the area of a triangle with side lengths A and B is given by A equals 1/2 AB sine theta. There's a little geometry fact for you. Molly missed the sip. Very sad. Okay, so if A equals 2 and B equals 3, okay, so this is given to us. If A equals 2 and B equals 3, and theta increases at a rate of 0.2 radians per minute. So what is that? D theta dt is equal to 0.2 radians per minute. We want to find how fast the area is increasing. So we want to find dA dt when theta is equal to pi over 3. Okay, so that's what the question asks. We have the area of a triangle with side lengths A and B is given by this. And the triangle we're looking at has one side length of 2 and the other one of 3. Okay. And we know that the angle is changing at a rate of 0.2 radians per minute, or whatever the units were. How fast is the area changing? Okay, so what we could do is just take our equation here. Here we're relating rates, right? This is a related rates question. Here we can take our formula here, take the derivative of both sides. Well, first, let's just plug in these values, 2 and 3. So A equals 1/2 times 2 times 3 sine theta, which is just equal to 3 sine theta. Okay, and we'll take the derivative of both sides, make sure we remember the chain rule, and plug in all the information that we're given. Okay, so the derivative, and we're going to do it with respect to time because things are changing over time. So the derivative of area with respect to time is equal to 3. What's the derivative of sine theta? It's cosine theta. Times what? D theta dt times the derivative of the inside. Okay, that's the chain rule here. Okay, and we want to find dA dt when theta equals pi over 3. So let's plug in all the information that we're given. dA dt is equal to 3 cosine pi over 3 times d theta dt is 0.2. So times 0.2. Okay, and so this dA dt is equal to 3 times, well, cosine of pi over 3 is what? 1/2, I think, times 0.2. And well, 0.2 is the same thing as 1/5. And so this works out to be 3/10. And so the area is increasing. Yeah, Cookie Man agrees it's 1/2. Yeah, sometimes I get a little bit, forget my units a little bit, but it is 1/2. So the area is increasing at a rate of 3/5 units, square units per minute. I don't think I gave a units for the side lengths. No, so whatever the length squared per minute. Okay, so this is basically we have this area is equal to 3 sine theta, and we want to just compare the rates, relate the rates. Okay. So I'll continue with that list of questions that I was asked to do, but if you have any ones in particular you want to see solved, just let me know in the chat. There's a bunch of questions. Beautiful and easy. Couldn't agree more. Okay, and I see there's a little bit of glare on these boards, so let's use the big board. So the next question that was asked for me is number 20. Another trig one. Okay, this is number 20. Is there a curve sketching one on the list that my students sent me? I don't think so. So maybe we'll do a curve sketching one. We'll do a curve sketching one after we complete the list. There's only a few more from the list. Okay, so number 20 is find the critical numbers of the function f of x is equal to 2 cosine of x plus sine of 2x. And then we're given the interval of 0 to 2 pi. Right? Because if there is no domain here, like with the trig functions, it could go on forever. Okay, so find the critical numbers. Okay, so as a reminder, before we get started on this, what are the critical numbers? Critical numbers are when our derivative is 0 or undefined. Okay, so a question that says find the critical numbers, it's just saying find when the derivative is 0 or find when it's undefined. Okay, so in order to find when the derivative is 0 or undefined, we should find the derivative. Okay, so derivative. Okay, derivative of 2 cosine of x is negative 2 sine of x. And the derivative of sine of 2x is 2 cosine of 2x. Okay, and this is just the sum of trig functions. And there's, sine and cosine they're both continuous functions. Right, so we're never going to accidentally divide by 0 or anything with these functions. Right? What's the point? This function is always defined. There's never a time when it's undefined. Okay, so to find the critical numbers, this is really going to boil down to finding when our derivative is equal to 0. So let's find when this guy here is equal to 0. Okay. So how do we do that? Well, we're going to use the trig identity. Okay, cosine of 2x. And if I asked a question like this on a test, I would give you the trig identity because we don't talk about trig identities too much in class. Actually, we almost never talk about it in class. Cosine of 2x is equal to 1 minus 2 sine squared of x. This identity you actually use quite a bit in Calc 2 when you're learning about integrals of trig functions. But you kind of rewrite it and have sine squared of x is equal to whatever it would equal. Okay, 1 minus cosine of 2x over 2. Okay, so we're going to use this. Yeah, Cookie Man sees it. So let's use this identity for cosine of 2x. So our derivative, f prime of x, is equal to negative 2 sine of x plus 2, 1 minus 2 sine squared of x. That's it, equals 0. Okay, and so we want to solve this. Well, let's rewrite this out. This is negative 4 sine squared of x minus 2 sine of x plus 2 equals 0, right? I distributed the 2 and just rearranged it. And there's a lot of 2's here, so let's divide everything by -2 to kind of clean it up. So we have 2 sine squared of x plus sine of x minus 1 equals 0. How do we solve this? So let me know in the comments. Let me know in the chat if you have any idea how to solve this. Yeah, quadratic formula could work. And the same idea, we could also just try to factor it, right? So quadratic formula, then you could also just try to factor. So I'm going to factor because it's going to be a little bit cleaner, but yeah, quadratic formula would work. Okay, so how does it factor? So we have a -1 here and a +1 here. Right? Okay, making progress. We have 2 things that multiply together. We have 2 things that multiply together that give us 0. Right? So that means at least one of them is 0. So there's 2 cases. Either this first thing is 0 or the second thing is 0. So let's start with this. So if 2 sine x minus 1 equals 0, that tells us that sine of x is equal to 1/2. Okay, when is sine of x equal to 1/2? That's pi over 6 and 5 pi over 6. Right, that's when sine of x equals 1/2. And when does sine of x, so the other case is sine of x plus 1 equals 0. So that means sine of x equals -1. When does sine of x equal -1? Well, that's when we're pointing straight down in the unit circle. So that's 3 pi over 2. All right, so yeah, more trick here. So we should just be careful. So that's when our derivative is equal to 0. You should just check that it's never the case that our derivative is undefined. There's no denominators or anything here. So our derivative is always defined. But yeah, critical numbers, remember, are when your derivative is 0 or when your derivative is undefined. Okay, so this was a case where the critical numbers only appeared where the derivative is 0. Now, if I asked a question that was like, find the absolute max or absolute min values of this function, what you would do is you would find the critical numbers, 1, 2, 3, all of these, and then you would evaluate the function at the critical numbers and at the endpoints, and you check which one's the biggest. That's your absolute maximum. Which one's the smallest? That's the absolute minimum. Yeah, cosine of pi is -1. Sine of 3 pi over 2 is -1. Okay, so a lot of tricks so far today, but again, I would give you some hints if I asked a question like this on a test, because we don't really talk too much about trig identities in class. Okay, let's continue on our list. So next up was number 37, so hopping down towards the bottom. All right, this is a good one. So those of you who are watching, maybe try this one. It's a fun one. So this is number 37, optimization. So find the equation of the line through the point 3,5, that cuts off the least area from the first quadrant. That's similar to one that black pen, red pen solved. So you should know how to do this, hopefully. Yeah, this is a good question. It's a bit hard. Yeah, it's not too bad. All right, let's see if we can get a picture going to see, okay, this is really not too bad. Okay, so what do we have going on here? We have the 0.35, maybe that's like here. I'll draw it a little bit lower, so maybe it's like here. And we have a line going through this point. And we want to cut off as little area as possible. Right? That's the goal. Minimize the area in the first quadrant. Okay. So let's kind of write out how we're going to do this. And again, I see the glare, so I'll move to here. I have this setup for the morning and like the early afternoon. I guess as it gets later in the day, the glare gets a little bit worse. But yeah, I teach here in the morning and then also at 1 o'clock. And the sun's is not too bad at those times. Okay, so the equation of this line, right? This line has some slope. So let's let m be the slope of that line. Right, we want to find the slope of this line that will make us cut off the least amount of area. Okay, so the equation of the line with slope m that goes to the point 3,5 is what? It's y minus the y component of our point is equal to the slope x minus the x component of our point. Right? And so what do we want to do? We want to minimize this area. So we should figure out how long this leg is, find out how long this leg is, and then multiply them together. And that's going to give us, well, half of that will give us the area. You're watching from Greece. It's 12:30 in the morning right now. Jeez. It's okay if you want to go to bed. That's pretty late. Okay, so how are we going to find this length and this length? Well, this length we should just find the x-intercept. To get this length, we need to find the y-intercept. Okay, so we need both the x-intercept and the y-intercept. Okay, let's rewrite this as y equals m x minus 3 plus 5. Okay. So we need the x-intercept and the y-intercept, and that's going to help us find the area of this rectangle. I mean, of this triangle, and then we could minimize the area based on m. Okay, so for the x-intercept. So the x-intercept, we have 0 equals m times x minus 3 plus 5. We need to solve for x. So x equals negative m over 5 plus 3. So negative 5 over m plus 3. Right, to find the y-intercept, we set x equal to 0 and solve for y. Okay, so that's y equals m times 0 minus 3 plus 5. So our y-intercept is negative 3m plus 5. So we want to find the area that we're trying to minimize is equal to 1/2 x times y. Right? So we want, this is what we want to minimize. Okay, so let's rewrite this a little bit. To try to make it easier to take the derivative, right? Because eventually we're going to take the derivative. Okay, so if we rewrite this FOIL, that gives us 15m over m. So that's just 15 first. So that's first. Outer is minus 25. I guess we'll call it minus 25m to the negative 1. Inner is minus 9m. Last is plus 15. Okay, so before we can get to the derivative, a is equal to 1/2. Okay, this is 15 plus 15, that's 30. So we have negative 25m to negative 1 minus 9m plus 30. Okay. So we want to minimize this, right? So how are we going to do that? We need to take the derivative, set it equal to 0 or undefined, and then test those values. Right, m could be really anything, right? It could be as steep as you want, or as shallow as you want. I guess 0 is like the lower bound, but there's not really a hard boundary for what m could be. So we just have to find the critical numbers. Okay, so let's take the derivative, a prime. Okay, the 1/2 can stay there. It's not doing any harm. What do we got? Positive 25m to the negative 2 minus 9, derivative of 30 is 0. Okay, so that's good. We have our derivative. Let's rewrite this as 25 over 2m squared minus 9 over 2. We want to get we want to turn this into a fraction, so we can find when it's 0 or undefined, right? If you get a nice common denominator, it's easy to check when it's 0, it's easy to check when it's undefined. Okay, so getting a common denominator, this is 25 minus 9m squared all over 2m squared. Okay, so if a prime equals 0, that implies our numerator is 0. Okay, solving for m, we get m is equal to 5/3 or negative 5/3. Right? Add over the m squared and divide by 9. But if it was positive, it wouldn't really cut off any, right? What would happen if it was positive 5/3? It would cut off no area in the first quadrant. Okay, so that's not going to be, I mean, I guess technically it says minimize the area, but we need it to be a negative slope. Okay, so we don't have to consider that case. Negative 5/3 is fine. That's going to cut off some area. And what's the other case? A prime is equal to 0. Right? That's a prime does not exist, and that would mean m equals 0. But we don't have to consider that case either, because the line with slope 0 would also cut off no area, right? It never cuts the region. So we only have one critical number, right? -5/3. Okay, so m is equal to -5/3. And I forget what the question even asked. Write the equation of the line, if that's what it asked. The equation of our line is y equals -5/3 x minus 3 plus 5. Okay, if you want to figure out how much area was actually cut off, you could plug in m equals -5/3 in for m in this equation. Just multiply it. And that'll give us the area. Could we use the second derivative test here? Yeah, sure. So if we took the second derivative of this to check that it truly is a minimum, so let's just check that, a double prime. So a double prime is going to be 1/2 of -50 m to the -3. Okay, and if we plugged in m equals -5/3, we would get a positive number. Positive second derivative means, oh, sorry, that's not what it means. Positive second derivative means concave up. So the critical number would be a minimum, which is what we were hoping for. So yeah, we could use the second derivative to check that this truly is a minimum. Right, because if we were to plug in m equals -5/3, we'd have a negative times a negative, which is a positive. Okay, yeah, that is a hard question. I'm sure Black Pen, Red Pen did a pretty good job explaining it also. Okay, and then so one last one from that list, but and then I remember there was an idea about doing a curve sketching one. So let's do number 40, and then we could look for a curve sketching one. Okay, we have a box with a square base and open top must have a volume of 32,000 cubic centimeters. Okay, art time, the Dr. Watson couch. It's always everybody's favorite time of the day. So we have a square base. See, here's a little tip for you. Okay, sorry, there's a car honking outside. Here's a little tip for you. If you want to draw a square base, you really want to draw it as a rhombus first, and then we'll extend it. And then I see Allie commented with number 33, so we can do that next. So is that a curve sketching question? I don't know, I'll take a look. Okay, so we have our square base. Yeah, let's do number 33 next, because it's curve sketching. Square base and then open top. So this top face doesn't exist in our drawing. Yeah, we'll do 33 for a curve sketching. So square base, so the base will be x by x, and the height will be y. Okay, right? The reason why it's x by x is because it's a square base, so that we know the length and the width is going to be the same. Height, we'll call something else y. It might also equal x, but we don't know that. Okay, so what are we given? We're given that the volume is equal to 32,000 cubic centimeters. Okay, the volume of a rectangular prism, volume of any prism actually, is the area of the base times the length here. So x times y. So x squared y is equal to 32,000. Right, and what do we want to do? We want to find the dimensions that minimize the surface area. Right, minimize the amount of material used. Okay, that's the surface area. So we want to minimize the surface area. So minimize, I guess I'll call it A for area. Okay, what's the surface area? We have a square on the bottom, x squared. And then we have 4 faces that are x by y, right? 1, okay, here we go, now it's going to be tough. 1, 2, 3, and 4. Okay, we have 4 x times y. And the top is hollow, right? I mean, or not there. There's no top. That was part of the question. So here is our surface area equation. And so we want to minimize this. So how do we minimize it? We need to eliminate one of the variables and then take the derivative, set it equal to 0. Right? So let's solve for y. So y is equal to 32,000 x to the negative 2. So our function a of x is equal to x squared plus 4x times 32,000 x to the negative 2. Right? So that's just the same thing as, well, a of x is x squared plus 128,000 x to the negative 1. Okay. So what do we do? Take the derivative, set equal to 0, find when it's undefined. So a prime of x is equal to 2x minus 128,000 x to the negative 2. Right, and this is 2x minus 128,000 over x squared, which we could get a common denominator and write it like this. Okay, so we want to check when is this 0, when is this undefined. Okay, so it's 0 when the numerator is 0. Right, a fraction is equal to 0 when the numerator is 0. Okay, so when is this satisfied? Well, we solve for x. We have x to the third is equal to 64,000. And so x is equal to the cubed root of 64,000, which double check me is 40. Okay, so the derivative is 0 when x equals 40. The derivative is undefined when the denominator is 0. So x equals 0. But we can't have x equal to 0 because our volume is 32,000, and if x was 0, our volume couldn't be 32,000, right? That one of the side lengths, two of the side lengths would be 0, so there'd be no volume. Another way to check is our area has x in the denominator, so x is not in the domain here, or 0 is not in the domain. So throw that one out. Okay, x equals 40 is our answer. So x is 40. How do we get y? We know y is equal to 32,000 over 40 squared. Which is 20. Okay, so those are the dimensions. 40 by 40 by 20. Not too bad, right? Okay, so what was the tough part? You got to get the drawing going and then recognize that there's no top, but that was just part of the question. Okay, number 33, curve sketching. So I guess on this part with the glare, I'll write out what all the constraints are, and then we'll try to sketch something that looks nice and pretty. Okay, so we want to sketch a function that satisfies the following. Okay, sketch a function that satisfies f of 1 equals f prime of 1 is equal to 0. The limit as x goes to 2 from the right of f of x is equal to infinity. The limit as x goes to 2 from the left of f of x is equal to negative infinity. The limit as x goes to 0 of f of x is equal to negative infinity. The limit as x goes to infinity of f of x is equal to, wait, sorry, this is negative infinity here. is equal to infinity. The limit as x goes to infinity, so positive infinity, of f of x equals 0 if double prime of x is positive for x greater than 2, f double prime of x is negative for x less than 0, and 0 less than or equal to x less than or equal to 2. Okay. Let's see if we can sketch this. Okay, yeah, sorry I see the glare, but this is question number 33 if you want to just open up the questions in the description. Okay, so let's just check off one at a time, see what we got going on here. Okay, so let me get a new marker. F of 1 equals 0. That means the point 1, 0 is on the curve. Okay, f prime of 1 equals 0 means we either have a local max, local min, or maybe it's a point of inflection at this point. So what I'll do is I'll just draw kind of a little horizontal line there to remind us that the derivative is 0 at x equals 1. Okay, the limit as x goes to 2 from the right is equal to infinity. So let's draw ourselves a vertical asymptote here. And we know that as x goes to 2 from the right, we go up to infinity. Okay, and as x goes to 2 from the left, we go down to negative infinity. Okay, we might have to shift our line a little bit to make it connect, but you get the point. The limit as x goes to 0, okay, so it doesn't say what side, so it comes from both sides, is equal to negative infinity. The limit as x goes to negative infinity is positive infinity. The limit as x goes to positive infinity is 0. The second derivative of our function is positive when x is greater than 2. Okay, what does that mean? It means it has this sort of shape. It has a concave up shape. It doesn't have to have the full cup, but maybe it has only half of it. And we can make that happen over here, right? Okay, so I'm happy with the right-hand side of our graph. Okay, for x greater than 2, it definitely satisfies all of our constraints. And what's this last part? It says our second derivative is negative, so we're concave down when x is less than 0, and also between 0 and 2. Okay, so we can just connect the dots here. Okay, that's good. And then we just got to make sure we're concave down going this way. Man, that's a pretty terrible drawing, but all right, let's do this a little bit better. Okay, that's concave down and going off to infinity. All right, so yeah, what's the point? You know, make sure it's a function, right? Sometimes people, when they get a question like this, they just like try to go one at a time. All right, let me first draw a graph that satisfies this property, and then like by the end you have like 15 lines going around. Don't do that. It should just be one function. It's okay that it's discontinuous because you'd expect it to be discontinuous with these vertical asymptotes. But yeah, you know, you just go one at a time, just check it off, make sure you're satisfying all the properties. And then at the end, you know, connect the dots if you can. All right, we have time for a few more questions, so if anybody wants to just let me know in the chat. I see somebody just gave me the like because they must have really liked this question. I don't blame them. So yeah, thanks whoever did that. Yeah, so let me know in the chat if there's another question you want to go over. So yeah, just as a reminder, what's on? I just joined. Oh, welcome. So as a reminder, what are we going to see tomorrow? Optimization, related rates, curve sketching, linear approximation. Number 18. 36. Okay, another curve sketching. Sketch the graph of the following that has, or sketch the graph that has the following properties. Okay, so the properties are, we want it to be continuous on the interval 1 to 5. Okay, so that's our domain. Absolute max at x equals 2. Absolute min at x equals 5. Okay, and then x equals 4 is a critical number, but no max or min. No local max or min. It's so cool that professors make live streams for students. Yeah, thanks. It's fun. It's fun. And hopefully my students find it useful. If not, they don't have to be here. Yeah, the video is blurry. Yeah, it's a little bit out of focus because of my autofocus, but I think overall, are other people having issues with the clarity? It might be just on your side, Alexa. Okay, so we want a function that's continuous on 1, 5, but I'll try to, oh, it's good now. So maybe it was just buffering. I'll write nice and bold so it's easy to see. Okay. Taylor, oh, I'm glad you're finding it useful. So it's continuous on 1, 5. So let's just write out the domain 1 to 5. Okay, so here's 1, and then over here's, maybe give some space. Over here's 5. So we should make sure we don't leave this interval. To make it even better, let's just kind of erase everything else. Okay, there is our interval. Okay, absolute min at x equals 5. So I know I said absolute max at x equals 2 first, but let's mark in the min because it's on the boundary. Okay, so down here is going to be the lowest our curve is going to hit. Absolute max is at x equals 2. So up here could be the highest. Okay, let's call that 2. Our curve could hit. And x equals 4 is a critical number, but no local max or local min. So there's a number of ways this can be done. So let me know in the chat if anybody knows. How can x equal 4 be a critical number, but there's not a local max or a local min there? What is a critical number? A critical number is when our derivative is 0 or undefined. Point of inflection. Yeah, you could have a point of inflection, and that could correspond to a critical number. Another way is if the derivative is undefined, so like you have a vertical tangent. Yeah, it seems like point of inflection is a good answer. Let's do point of inflection because that's probably a little bit easier to draw. So yeah, let's maybe this could be 4. And here's our point of inflection. Okay, so what does it mean to be a point of inflection? It means it goes from concave up to concave down, or vice versa. And so yeah, now we can that's it. So let's just connect the dots. Let's maybe make that a nice, smooth. You can't tell, sometimes it's hard to draw on the whiteboard. Okay, and then just to make it clear to the grader, point of inflection, Or okay, and then also like horizontal tangent. So yeah, so we have a horizontal tangent and a point of inflection. That's a good way to get a critical number of 0 and yeah, not get local max or local min. You can't have a vertical asymptote because it's a continuous function. Yeah, but you could have a vertical tangent, right? You could have something like this, right? Because so here the function is continuous, but the derivative is not continuous. Yeah, so a vertical tangent is fine. A vertical asymptote would not be fine. Okay, but yeah, so on a question like this, just make sure you check them off. Easy points, right? Continuous on 1.5. You don't know the number of people that would just give me a discontinuous function. So come on, man. All right, so continuous, boom, good. Local max or absolute max at 2, good. Absolute min at 5, great. And then this is the tough one, but we got it, right? A little hard, but we got it. Okay. Let's do one more. So if anybody that's in my class has a question, type that into the chat. But if not, anybody else can just ask a question. It's fine. But I'm going to give priority to students in my class. I know there was one asked earlier, but it's vanished on my screen. So I think Molly asked it. I don't remember if that was number 36 or something else. Yeah, and again, so we're not artists. Yeah, 36. Okay, we could do artists. We could do 36. We're not artists, but the idea is if you label, okay, this is a horizontal tangent and a point of inflection, then it's clear to me that you at least know what you're trying to aim for. Okay, 36. Anybody in my class, if you want to not do 36, now's the chance. I know there's a little bit of a delay, so let's look at 36. Okay. Okay, I'm gonna veto 36 because we did it in class. But we could do something similar. Let's do a distance one. At which level do you teach math? This is college math. Yeah, this is a Calc 1 in college. Some people take Calc 1 though as a senior in high school, so it's kind of like a borderline class, but typically people will take it in college. All right, I'm going to do a different optimization question. Molly, I know you asked for an optimization, but I'm going to do a slightly different one because we just did that last one in class. So I want to find the point on the curve. So find the point on the curve y equals, y plus 2x equals 4. So find the point on the curve that's closest to the 0.50. I don't know how it works in the US, but it's different in France. Yeah, every country does it a little bit differently. But yeah, typically in the US, some students will take calculus in high school, but a lot of them will just take it in college. Okay, so we want to find the point on this curve. This is actually a line, but we call it a curve. That's closest to 5,0. So what do? And this is the last question on the review, actually. 44 question review. A little bit long. Okay, so we should just find the distance between any point, right? The distance between any point in 5,0 is given by the distance formula, right? It's x minus 5 squared plus y minus 0 squared. Right, we want to minimize this. Okay, and so this is x minus 5 squared plus y squared. What the square root of all this? And we don't know how to minimize functions of two variables. You gotta wait until Calc 3 to do that. So what we could do is solve for one of these variables and plug it in. So let's solve for y. We can plug that in for y. Okay, so if we solve for y, we get y equals minus 2x plus 4. Okay, so we're trying to minimize the function, the square root of x minus 5 squared plus negative 2x plus 4 squared. Okay. Does this have something to do with an equation of the circle? Yeah, I mean, this distance formula really comes from the equation of a circle. A circle is a set of points that are like the same distance from the center. Can't we just set delta to be the distance between 5, 0 and the line? Yeah, so that's what we have here. So here we made it the distance between, so we started the distance between any point in 5, 0, and then by subbing in the equation y equals negative 2x plus 4, that's restricting all the points to be on the line. Okay, so now we're on the line. And what's nice about the square root function is to minimize the square root is the same thing as just minimizing the inside of the square root. So we could just deal with the inside here, which we'll call capital D. Okay, so to minimize distance, it's the same thing as minimize the inside of the square root. Okay, and so to minimize this, what do? Take the derivative, set it equal to 0. The derivative is 2, x minus 5, times the derivative of the inside, which is 1, so chain rule, still there, plus 2, negative 2x plus 4, times the derivative of the inside, which is negative 2. Okay, chain rule coming in again. Love the chain rule, absolutely love it. Okay, so we want to clean this up and we'll set it equal to 0. All right, so this is 2x minus 10. And what do we have? 2, negative 2, 2. That's plus 8x. And minus 16. All right, if I didn't make any algebra mistakes, I'm feeling good about this. Equals 0. And now we can combine them. So 10x minus 26 equals 0. And we have x is equal to 26 over 10, which is 13/5. Okay, so the point that's closest to the point 5, 0 has an x component of 13/5. And how do we get the y component? We just plug it in to this guy here. Okay, so I'll do that up here. Okay, and so we get y is equal to negative 26/5 plus 20/5, which is equal to negative 6/5. So what point is closest? What point is closest to the point 5, 0? It's the point 13/5, negative 6/5. Okay, and if you wanted to find what that distance was, how far is this point from the point 5, 0? You could just plug this into our distance formula here. You know, to give you the distance, but I didn't ask for the distance, I just asked for the point. Okay, I'm gonna call it quits. So those of you who are in my class, good luck tomorrow. You know, get a good night's sleep, you'll do fine. I tried to make the test a little bit shorter than the last one, so hopefully everybody can finish on time. Those of you who aren't in my class, thanks for coming. This was a lot of fun. We'll probably do another one before test 4, which is in a couple of weeks, and then who knows what we'll do before the final, but maybe we'll go longer than the hour that we've been doing for this. All right, so see you later. Thanks for coming, and have a good day.